Okay. Now I said I would start with solids of revolution because people asked me about that last week. And I'm not entirely sure what those people actually wanted, and we'll see if what I do is good enough and then ask them if that's what we wanted. And sharpen my pencil so it doesn't dry. Okay, so your basic solid of revolution is actually a special case of a bigger idea, which is that you can find the volume of a shape by slicing it into slices. So, for example, a cone, you can slice it with a plane at various heights and get various circles. And what you do is you imagine that you stack up all those circles to produce your cone. Okay? And so you're imagining that your cone is actually constructed from a whole lot of very, very thin slices. And you can do this regardless of whether they're circles or not. A pyramid is the same kind of idea. So you can stack up a whole lot of squares on top of each other to make a pyramid. So the basic idea of this is that you want to find a way of slicing it into pieces so that you have a formula for what the area of that slice is at each height. And then you can add up all of those areas and that will produce a volume. But of course, adding up infinitely many things is what integration is for. So way back in Maths 1A, when we did upper and lower sums, we were creating areas, we were finding the area of an object by stacking up a whole lot of very tiny rectangles. Well, now we're finding the volume of an object by stacking up a whole lot of very thin slices, and it's the same idea. You just need a formula for what the volume of that tiny slice is. Okay. But for solids of revolution, they're created by revolving something around some line, and so those slices are always circular. And so, with a pi in the formula. But the same idea happens. I just wanted to generalise that, because in the assignment there was one about a shape that had equilateral triangles. As it slices, you could do anything to produce those slices, and as long as you can find a formula for the area of that slice, you can find the volume. Right. The basic idea of this is that the total volume is the integral from some place to some other place of the area of the slice times dx or dy or something. Okay? That's the basic idea of it. And this bit here is the volume of your very thin slice. See, the volume of a slice is area times thickness, and that dx is a very tiny change in thickness. Like it's a very tiny change in the value on the x or y axis, and it produces the thickness of the slice. So that's the idea behind it. As long as you can find the area of that slice, any method you use is fine. Okay? So what you need to do is figure out what line tells you how big the area is. Because with the squares, if I knew how long this was, it would tell me the area of a square. And then with the circles, if I knew how big the radius was, it would tell me the area of the circle. So each shape should be based on the length of some line somewhere. And so this area of the slice will change depending on how high up or how far across you are. And the only way that this makes sense is to do it as an example. So I'm going to do that, but that's the general intro to it. So example, the volume of solid obtained when you rotate the area between, here we go, y equals Did you just lose picture? No. Okay. Y equals x squared plus 1 and the x-axis between x equals 1 and x equals 2 around the x-axis. Volume of the solid obtained when you rotate the area between y equals x squared plus 1 and the x-axis between x1 and x equals 1 and x equals 2 around the x-axis. Awesome. That's probably not a very grammatically correct sentence, but it'll do for now. Each part of this describes something different. So one part of this, which is this bit here, is just, no, it's not very bright, is it? This bit here is the bit that tells you what the area is that you're rotating. And quite a lot of what's written there is telling you about what that area is. And we're going to need to draw that area before we can know anything else. And then there's another part which tells you what you're rotating around. The x-axis. Okay? So the first step is to draw this area. So we have y equals x squared would be that, x squared plus 1 would sort of be like that. We have x equals 1 and x equals 2. And that's the area that we're going to rotate. Awesome. So we also need to know what we're rotating around, and we're actually going to rotate around the x-axis. So I like to draw myself a little rotating circle thing with an arrow that tells me what line I'm rotating around. So what's going to happen is this. I'm just going to move that up so I have a bit more space to do what I'm about to do. So we're going to get that shape. I'm going to cut it out. And this bottom edge here is what was on the x-axis, and it's going to get rotated around the x-axis like that. So it can go round this way from above, you can see it that way. So the shape that's created is sort of like a volcano, sort of. It's going to produce sort of something like that. Okay? So now we've understood what's going on. Right. Now, we do not need to know the area of this shape. That shape. The area of that shape is completely irrelevant because I'm going to create this volcano shape by slicing it up into circles. Okay? And I need to know the area of those circles, not the area of this shape. Okay? This shape is irrelevant. It just tells us where the stuff is that does crap, it's backwards. Damn. It won't make any sense to people who weren't that way. That's better. Okay. So what we need to do is we need to figure out at every place along this x-axis, so here along the centre of my shape, how big the circle is at that spot. And once we've got a formula for how big the circle is at that spot, we can integrate it and it will tell us the volume. So we need to know, sure, this whole shape produces this whole volume, but we want to know over here what becomes the circles that are over here. So this vertical line here, when it's rotated, becomes this circle here. And this vertical line here, when it's rotated, becomes this circle here on the bottom. And a vertical line somewhere in the middle becomes a circle somewhere in the middle when you rotate it. Because you can imagine, when I draw that line and I rotate it, it sweeps out a circle in space. So it's those lines that we're interested in. So when we solve these problems, we want to look at the vertical lines that are drawn on our picture. So this vertical line here, it's going to have a different length depending on what x is. So I'm just going to say that that's at position x. And then this height here Well, that's the height of my function. My function tells me how high up to go for a particular x, so that height there is x squared plus 1. So when I do my rotating, what happens is that this length here becomes a circle. Technically it goes around this way in space, but I'm just going to draw it like that. And that there is x squared plus 1. So that's the radius of my circle. So the area of my circle is pi times x squared plus 1 squared, because it's pi times the radius squared. And that's the area of my slice, and all I need to do is integrate them, and it will tell me what the volume is. So the volume will be the integral from 1 to 2, because that's the numbers that tell me what x is, of that area. So technically I could have put an extra line in there that says sort of the volume of the slice, which is the area times the thickness. And that's a sort of statics engineering sort of thing to do. If you ever saw how they calculated centres of mass in statics, they do that sort of thing. So that's not very important. I just need to say it there in case someone said it to you before. So this is the volume of the slice that's actually like a little tiny, very thin disc. And the thickness of the disc is dx. That's the idea behind what we're doing. And then this sum sign, this is actually just adding up all those little slices. So now that's pretty straightforward, hopefully. Oh, I should expand out those brackets because that'll make my life easier. And I'll get integrating, aren't I? From 1 to 2, and then I'll sub them in and it will tell me the answer. So yeah, whatever. Just to be absolutely clear about what's going on there. So that is the actual final volume, whatever that works out to be, pi times something. 32 on 5, 6.4, 230. I'm not going to do that in my head. Didn't even bring a calculator, which is, you know, the answer. Right? Whatever that is. Okay, but that's how you calculate it. Right, and everyone's saying to me, but David, I already knew how to do the one that was around the x-axis. What if it's right around the y-axis? What if it's around some other line that's not the x-axis? That's what I really want to know, because that's the bit that really confused me. So I better talk about that. And I've still got a few minutes before I need to launch into the other bit, so let's go there. Okay, but just to be really clear, the major part of your work in solving this problem is here. This stuff is just integrating, you know. But, you know, just in inverted commas integrating. You have to remember Maths 1A, of course. But the hard bit is here in figuring out what produces the area that you're looking for. Okay. So let's do our next example. As usual with these seminars, I'll photocopy these and put them online as a PDF in case you don't want them. Okay, so what if we alright, let's see, we're going to rotate, I don't know, y equals 1 over x between x equals 1 and x equals 3 around the line y equals 2. Right. So I should say the area between, shouldn't I? The area below y equals 1 over x between x equals 1 and x equals 3 around the line y equals 2. Cool, so we've got the same trick again. This bit is describing the shape that we're rotating to produce our 3D shape, and this is the thing that we're rotating around. Now y equals 2 is a horizontal line, but this time it's not actually inside my shape. So let's draw that. So 1 over x is sort of that shape, and we've got 1 and 3. So this shape here, but we're not rotating around the x-axis this time, we're rotating around the line y equals 2, which is sort of up here somewhere. Because that's 1 there, right? That's 1 over 1. Okay, so what we're rotating around is this line. So what happens is that we end up with a big gap in the middle of our shape. Because when we do that little thing that I drew, so this is my shape, right? But what we're doing is we're rotating it around this line here. So when we rotate, got to be in screen. When we rotate around that line, you sweep out something, but all that white space is just a hole in the middle of my shape. So I've tried very hard to colour it in on the other side when it sweeps the other way. So it was like this. I swept it round this way, and it came down here, and I swept it back around here until we started. And we ended up with a shape around here, but there's a hole in the middle. So we need to be able to account for that hole as we create the shape itself. So what we're going to do is we're going to draw a vertical line again. So I'm just going to draw a dotted line up here so we can see where the hole is. And this time I'm going to draw my vertical line again. It has to go from the bottom of my shape all the way to the thing that I'm rotating around. So we have a vertical line here and there. And it's rotating around that dot that I've drawn. And this is at position X here. So, all right, that vertical line there, here, that, when rotated, is going to produce this. Okay, so I've got that and then the dotted line there. Okay, so this is a copy of that line there. And so that dotted line bit makes a hole in the middle of my circle. And it's this that is the slice of my solid shape. Because then I stack all them together to produce so in the centre of my shape, there's sort of a hole that gets narrower and narrower as it goes along. Crap, no. It goes wider and wider. I hate drawing 3D shapes. Which totally makes no sense whatsoever, which is why this doesn't help. But it's this line that sweeps around to produce a circle here. So that dot there is the dot that's on that line y equals 2. This here is that bit there, and this is that bit there. So the only way to find the area of this, the official name for this shape is an annulus, is to find the area of the big circle and subtract the area of the small circle. And you have to do this subtraction before you do the integral, because we have to do the area before we do the integral. So the area will be, well, just need a bit more space, area will be the area of the outside circle minus the area of the inside circle. Okay, so my outside circle has this radius here. That's the radius of the outside circle. And that radius from my other picture was over here, and that distance is 2. On my picture, it's from the x-axis to y equals 2. So that's 2 there. And this dark line here is that dark line just there, which is the height of my function. So this is 1 over x. Which means that this radius just here must be 2 minus 1 over x. Now found all the pictures. So the area of my outside circle is pi times its radius squared. And the area of my inside circle is pi times its radius squared. This length here isn't the radius of a circle, it's that length and that length. So what I've used here is my area of my outside circle is this bit here, the orange bit, and the area of my inside circle is this bit here. Those two radiuses, or radii, produce the areas of the circle that I want. And this is what I integrate. So I've got 4 pi minus pi times that's what I'm going to integrate. So my volume is going to be the integral from 1 to 3 of this area. Oh look, there's another 4 pi there, which is sort of cool. Dx. And that is what the volume is going to be. And from this point, we can ignore everything else that it was and just look at this as a brand new integration problem. The 4 pi will become 4 pi x, because 4 pi is just a number. This will become ln, and that'll be 1 minus 1 over x. Minus 1 over x. No. Yes. And so we'll rewrite it in a way that means that we can integrate it. Okay? And so you can... blah, 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 blah. Right. So, did anyone ask Michael whether he expects you to be able to rotate around the y-axis in the exam? No? Would you like me to show you? Yeah. The y-axis is a whole different story. When I did Maths 1, this was before there was Maths 1B, and it was just a full year course, and it was called Maths 1, which makes me sound old. I can't be old because my oldest staff member who works in the Maths Learning Centre is 73, and I can't be old until I'm as old as him. My daughter and his daughter have their birthdays on the same day, but 40 years apart. So, yeah. So I can't be old until I'm as old as him. And he'll always be older than me, so I'll never be old. So, until he dies, I suppose.
Are you younger than his daughter?
Am I younger than his daughter? Yes. Yes. So, yeah, he's quite old enough to be my grandfather. Well, maybe not my grandfather. At least my dad. Yeah, he's older than my dad. So, anyway, that was a stupid diversion. Let's move on to another example. We're going to rotate around the y-axis. Now, rotating around the y-axis can be hard in a number of different ways. Okay, so yeah, I was taught a method when I was doing first year called the method of cylindrical shells, which is really totally awesome and very easy, but you haven't been taught it, so I don't want to teach you now. Okay, but one day, if you're doing, say, water engineering or something like that, and you have to model the flow through a pipe, you may be given an assignment that, that the solutions use the method of cylindrical shells. So if that method of integration to finding a volume doesn't make sense to you at the time in third year, come back to the Maths Learning Centre and I'll tell you all about it. What if we're going to rotate between, I don't know, let's see if I've got one that actually makes the slightest bit of sense. 1 over x, y equals 2, and x equals 2 around the y-axis. Okay, and find the volume produced. So this time, I've got my region, and I've got the y-axis this time. All right, so first I draw my region, just like I always do. There's y equals 1 over x. There's y equals 2. There's x equals 2, and that's the region I've been asked about. It's the region between those three lines. So don't be fooled, and for Stephen's benefit, beware of the toast. You can look at my blog to know what that's about. Don't be fooled when you do this sort of problem that it's always between some point lines on the x-axis. It could be between various lines, so read it really carefully and note what's going on. And we're rotating around the y-axis here. Okay, so I'm rotating around this line right here. Okay? So this time when I produce my shape, it's rotating this way, and so the lines that will become my circles are actually horizontal lines, because the centre of my circle is at the line that I rotate around. It's rotating this way, and so it's this horizontal line that will become my circle. So thinking about saying, well, the centre of my circle will be on the line that I rotate around, and I need a line perpendicular to that, and so they're horizontal lines. And so to know what the length of this line is, or the radii of those circles is, I have to know what the y-coordinate is, because it's touching the y-axis. So I need to convert everything to be in terms of y instead of in terms of x, so that I can do this problem. And so, firstly, I need to know which zones, or where it goes between on the y-axis, so I need to know what this point is. So, point A is the intersection of 1 over x and x equals 2. So we've got y equals 1 over x and x equals 2. So we get y equals a half. Cool, so my integral is going to be a half up to 2 because that's y equals 2. That's good. And now I need to know what the formula is for any length that's in this picture. So this distance here is 2. So that's good. That's going to be my outside radius. My inside radius in the hole in my ring is going to be the distance from here to here, and I need to figure out what that is. So, if y equals 1 over x, that means that xy equals 1, so x is 1 over y. So that means that this distance here is 1 over y. If that's the y there, that is 1 over y. So my shape is my line is going to become a circle. The centre is here. So that's my line that's there. And I rotate it around the y-axis to produce a circle with a hole in it. And this distance here is 1 over y. And this distance here is 2. And this distance here is 2 minus 1 over y. So my area is the area of the outside minus the area of the inside and that would be pi times, no, that would be pi times 2 squared minus pi times 1 over y squared. No, crap. Yeah, that's right. So this time the inside circle is just 1 over y. It's not the 2 minus whatever. I don't need to know what that is, but I just put it in there while I was doing stuff. So this circle's 1 over y, that circle's 2, and I can integrate that now. So the volume must be the integral from 1/2 to 2 dy, because I'm moving up and down the y-axis. And I get that. Do some algebra, do some integrals, and there's my answer at the end. Okay? So I don't remember, when I do this, maths, it's not very useful to just remember a zillion different methods for all the zillion different problems you could be given. You need something that's going to work for everything. And for me, drawing my vertical or horizontal line, saying where's the centre of my circle, it's on the line I'm rotating around, where's the line that's perpendicular to that, that's going to be the radius of my circle. Drawing the circle, figuring out its radii, that's the method that I go through. So I've got the step where I draw the picture and find the length that becomes a circle, draw the circle, find the area of the circle, possibly minus a hole, and then you'll integrate that to get the answer. Cool, got about 20 minutes, possibly a little bit longer. Right, before I move on from that, any questions about integrals or rotation? Awesome. You can always come to Maths Learning Centre today, or if you're extremely desperate, the hour or two before your exam tomorrow. When is your exam?
Thursday.
Oh, on Thursday, because we won't be there tomorrow. We'll be training the School of Maths tutors for doing their job, hopefully better, next year for your, people who come after you. So maybe if they're teaching engineering about maths, it'll be better for you in the end. Right, just give me a minute. I'm actually going to stop the video so that I can do a separate one for the other bit I'm going to talk about. So.